The question is, could you explain the position vector method of resolving a 3D force vector into components? We mentioned in another video that there are at least 3 different ways to find the components of a 3D vector: the projection method, the direction angle method, and the position vector method. So in this video, we're going to talk about this third method. We also talked about how to define a 3-dimensional Cartesian coordinate system. I'm referring to the video on the projection method. So if you haven't seen that video, I recommend that you do that first. There is a right way to do it, as in this picture, and there's a wrong way to do it, as in this picture. Let's start with the fundamental question of what is a position vector. Let's consider 2D for now. So in this 2-dimensional space, let's say there's a point A, right, which has coordinates x1 and y1 with respect to this 2-dimensional Cartesian coordinate system. Now if I were to draw a line connecting point O, which is the origin of the coordinate system, to point A, and call that as vector RA, vector RA is what is defined as the position vector of point A. Now supposing, say, there's a general vector of A which doesn't start from the origin, but it starts from point A. It goes from point A to point B. The vector going from the origin O to point A is the position vector of point A, and similarly the vector going from point O to point B is the position vector of point B. Supposing, say, the coordinates of point A and point B are given. The question is, can I find a unit vector along A? If I could, then the vector A can be represented in its component form by this method. Vector A equals the magnitude of A multiplied by the unit vector along that vector, right? A force vector, which is what we are interested in this section, can then be represented by this method. While this type of approach is really useful for representing a 3D force vector, let's start with a 2D force vector first in order to understand the fundamentals. So here's the picture one more time, the one that we looked at in the earlier slide. We have a vector A that goes from point 1 to point 2, and the coordinates of point 1 are x1 and y1, and the coordinates of point 2 are x2 and y2. Let's go ahead and construct this triangle in terms of the projection of A along the axes x and y. We see from the picture that this horizontal distance is the horizontal component AX of the vector A, and from the geometry we see that AX equals x2 minus x1. And similarly, this distance is y2 minus y1, and that is the y component of the vector A. By the Pythagorean theorem, we see that the magnitude of A is simply square root of ax squared plus ay squared. The vector A in its component form is this, ax times I plus ay times j, which can be written like this. We know that vector A can be written as its magnitude multiplied by the unit vector along that vector. Now by comparing the left and the right sides of this equation, we see that the unit vector u equals ax over a times I plus ay over a times j. So we achieved what we set out to do. We found the unit vector along the vector A whose n coordinates are given. So all we have to do is to find the components first, and then find the vector going from point 1 to point 2, and then divide that vector by the magnitude of the vector A. Now let's extend the method to a 3-dimensional vector A going from point 1 to point 2 like shown over here. The coordinates of point 1 are x1, y1, z1, and coordinates of point 2 are x2, y2, z2. Now picturing a rectangular box around the vector A, like shown in this picture, you can see the dimensions of this box are the components of the vector A. The dimensions of this box are these. Ax equals x2 minus x1, ay equals y2 minus y1, az equals z2 minus z1. The magnitude A is then given by square root of ax squared plus ay squared plus az squared, and the unit vector along A is ax over a times I plus ay over a times j plus az over a times k. Now let's say we have a force F whose direction coincides with the direction from point 1 to point 2. Let me emphasize that only the directions coincide, not the magnitudes. If you're wondering about a problem where we run into a situation like this, here's an example. We have a vertical tower that is supported by two cables like this. The tensions in the cable are known. This one has a tension of 2 kilonewton and this one has a tension of 3 kilonewton. We also know the coordinates of the endpoints of these two cables. In other words, the magnitudes of the two forces in these cables are known, and we need to find unit vectors along the lengths of these cables on the basis of the coordinates of the endpoints. Here are the details of representing the force in terms of its component form. Using the theory we talked about earlier, we find the unit vector by these equations, and then vector F will be simply equal to magnitude of F multiplied by the unit vector from point 1 to point 2.